Our definition of a vector space was supposed to generalize ordinary column vector addition and scalar multiplication, and that definition consisted of a list of axioms which were familiar properties of column vector addition and scalar multiplication. But there are some familiar properties of column vector addition and scalar multiplication which aren't on that list of axioms. For example, if you give me any column vector, like for example the column vector 1, 2, and if you then scalar multiply that by 0, then I know that you'll always get the answer, the 0 vector. But that property isn't on our list of vector space axioms. So if we want to know that that property is true in every vector space, not just vector spaces consisting of column vectors, then we need to give a proof only using the properties that any vector space has. In other words, using the vector space axioms. So let's begin by doing that example. I've written for you on this slide the vector space axioms in the bottom right, and we're going to use those vector space axioms to prove that in any vector space whatsoever, if you multiply a vector by a scalar, by the scalar 0, then the answer is always the 0 vector. So let me clarify a little bit before I do that. When I say vector, I mean element of this vector space. As we've seen, elements of vector spaces don't have to look like vectors. They can be anything at all. But we will use the word vector simply to refer to an element of a vector space, regardless of what kind of thing it is. So let's begin with this proof. On the left-hand side of that equality, I've got the scalar 0 multiplied into the vector v. And my convention for writing vectors is I'm going to underline them to make sure there's some kind of visual distinction between vectors and numbers. So I'm multiplying the number 0 into this vector v. And I can write this as 0 plus 0 multiplied into v, because 0 plus 0 is equal to 0. And we can then multiply things out. So if you take a look at axiom 7, it says that scalar addition distributes over multiplication. So I can rewrite this as 0v plus 0v, where the reason this is true is because of axiom 7. So ax is short for axiom here. Okay, what can we do now? I want to cancel basically one of those 0 times v's from both sides. And the way cancellation works is, well, cancellation is like adding the additive inverse to both sides. And there is an axiom that helps me with that. So axiom 2 says that there exists a vector a vector x, such that if you add x to 0 times v, then the result is the 0 vector. Okay, so let's take that x and add it to both sides. So on the left I will get x plus 0 times v, and that is something we can easily simplify. On the right we've got something which is not quite so easy. It needs one further step, and it's this. Okay, so on the left I know from the definition of this thing x, I know I've got the 0 vector. And on the right I'd like to be able to simplify this, and in order to do that I need to use the associativity property. So I can use associativity axiom 3 to rewrite this by moving the brackets. So this is axiom 3. Okay, so one further step. What have we got on the left? We've got the 0 vector plus 0 times v, and that's just because of the definition of x. And then finally, this is just the 0 vector added to something, so it's just this by axiom 1. Okay, we've proved this result. Let's do one more, which says that if you've got a vector space v and an element x of v, then if you add x to minus 1 times x, that's the 0 vector. So it's saying that in order to get the additive inverse of a vector, you can just multiply that vector by minus 1. Now, nothing in the axioms immediately guarantees that, but we can prove it using the axioms. So let's see how we might do this. So the problem is with this expression x plus minus 1 times x, is it doesn't really fit into the left-hand side or right-hand side of any of my axioms. So it's not really clear what we should do to transform the whole thing. What we can do is just transform one part of it. So if I were to change that x into 1 times x using axiom 5 here, then I could then use a distributivity axiom to simplify it. So 7 and 8 of the distributivity axioms. So let's use axiom 5 to say this is 1 times x plus minus 1 times x. Okay, so then I can use axiom 7 to say this is 1 plus minus 1 times x. Okay, 1 plus minus 1 is 0. And you know that multiplying by the 0 scalar gives you the 0 vector by the previous lemma. Okay, we are done. We've shown that x plus minus 1 times x is the 0 vector. And so you can find the additive inverse just by multiplying by minus 1 in any vector space you like.